Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So, in this video, we're going to learn about the most important topic in the graph series, which is the disjoint set data structure. It's a very important topic. Why? This is commonly asked in almost all interviews and the online assessments as well. So, you need to master this topic. And in order to master this topic, you have to watch this video and all the follow-up problems that I'll be solving in the next part of this graph series. So, let's understand why is disjoint set data structure used. So imagine I give you something like 1, 2, 3, 4, and I give you other portion like 5, 6, 7. This is a single graph, but it has two components. First one is this, second one is this. Now suddenly someone will come up and say, hey, does 1 and 5 belong to the same component or not? How will you determine? You'll pick up 1 and you'll start a DFS traversal. 1, 2, 3, 4. And the traversal is complete. You could not find 5. Since you could not find 5 in the DFS traversal of 1 in that component, you'll be like, they do not belong to the same component. You did a DFS traversal and that's the brute force. How much time will the DFS traversal take? N plus E. That's the complexity the DFS or the BFS takes. Already discussed this in the previous section of the graph series. If you do not know DFS or BFS, go back and watch it. So the brute force is going to take a kind of linear time complexity. So this is where something like disjoint set comes in and says, hey, I'm going to do the same thing in constant time. You ask me, does 1 and 5 belong to the same component? I'm going to tell you in constant time, either a yes or a no. That's the use case of disjoint set data structure. And one more thing, it is usually used in dynamic graphs, graphs which keep on changing, their configuration at every moment. What do you mean by exactly changing configuration? I'll explain you that in the later part. So disjoint set gives us two options. One is finding the parent. That's one of its main functionality. And the other main functionality is union. Now, this union can be done with two methods. One is rank, other one is size. I'll be discussing both of them. But so primarily it gives you two functions, find parent and union. Now, I did talk about dynamic graphs, graph changing configurations. So let's understand this. Now, what do you mean by these things? These are all edges. There's an edge between 5 and 6. Okay. So initially, what we assume is 1, 2, 3, 4, 5, 6, 7. Everyone is alone. So initially, before all these edges formation, every node is single, right? So you have 1, 2. What it means is I'm asking you to connect 1, 2. So that is what union does for you. Remember this. Whenever I say connect 1, 2, union in disjoint set will do it for you. We'll talk about union in details, but as of now, know the higher level of union. Union will go and connect this. So what I'll do is I'll go and connect. Okay, done. Next, 2 and 3, connect 2 and 3. Next, 4 and 5, connect 4 and 5. Next, 6 and 7, connect 6 and 7. So you see the graph is changing at every instant. But you'll be like, but Striver, wait, this is how graph is formed. But what happens here is if I stop the formation over here and I give you a question where after this formation, I suddenly ask you, hey, does 4 and 1 belong to the same component or not? You will say no. Why? Because 4 as of now is here, 1 as of now is here. Till this point, they are not in the same component. So the answer will be no. So in any stage, someone might come up and ask you because the graph is changing at every step. But I can ask you a question at any step and you should be able to answer that in constant time. That is what disjoint set will do. And I'll explain you how it does. Next, 5 and 6. Let's connect 5 and 6. Next, 3 and 7. Let's connect 3 and 7. Now, if I ask you the same question, does 1 and 4 belong to, like after performing all the operation, does 1 and 4 belong to the same component? Your answer to that will be yes, they do belong to the same component. Understood? So you saw till here the graph was something different. The moment you performed the next two operations, the graph was a combined one. So I can ask you this particular question, or any U and V belong to the same component at any particular time. So this is the use case of disjoint set data structure. Now let's quickly check out what is find parent and what is union exactly. So in order to implement a disjoint set data structure, we can implement union in two ways. One is the rank, the other one is the size. So I can follow two ways of doing it. Okay. But initially, I'll be teaching you the rank, I'll be coding you up, showing you how to write a clean code so that it can be reused in almost all the problems. And then I'll be teaching you the size one. So the video will be like first union by rank, then union by size. Okay. So let's understand rank. So in order to implement union by rank, we will be requiring a couple of arrays. One is the rank array, while the other one is the parent array, which will serve for finding parent. I'll explain you. So let's quickly assign the rank and the parent arrays. Okay, so the initial configuration is very, very simple. What we do is we assign a rank array with the same size of the number of nodes. Since the graph is one based indexing, I start the array from one. So everyone is assigned to 0. Okay, so what does rank 0 mean? So if you see this particular node, there is no one beneath it. So it means there is no one beneath it, 0 nodes beneath it. But eventually, with the optimizations that we will do, the meaning will change. So I'll explain you throughout the course. So now we have a parent array. Now remember, initially everyone is the parent of himself. Now what does parent mean? Parent, parent. Okay, right above guy. That is what is the definition of the parent, which is stored here. Again, over the course of this lecture, the definition of parent will change as we do multiple optimizations in order to obtain a constant time complexity. So this is what we currently have. Let's quickly start the operations. So let's quickly write the pseudocode for the union of u comma v. So remember, the step one is very, very simple. The step one says find ultimate parent. Yes, find ultimate parent of u and v. What is the meaning of ultimate parent? I'll explain you. And we can term this as ultimate parent, like ultimate parent of u and v. Let's term this as pu and pv. Pu means ultimate parent of u, pv means ultimate parent of pv. Now find rank of those ultimate parents. Find rank of pu, pv. Find rank of ultimate parents, not u and v. Ultimate parents. Okay. Now connect smaller rank to larger rank. Connect smaller rank to larger rank always. In case of equality, you can connect anyone to anyone. We will explain that as we move. Okay, cool. We have understood, or I've written the pseudocode. Okay, let's now quickly check out the first operation that has been asked for us. It says union of 1, 2. So what I do is I have 1. So I go and look at the parent of 1. What is the ultimate parent? You have a bunch of nodes. The guy at the top is known as the ultimate parent. Okay. So for 1, who is the ultimate parent? 1 itself. For 2, 2 is the ultimate parent. So I can say, as of now, the ultimate parent of 1 is 1 and the ultimate parent of 2 is 2. What is the rank of both? Can I say the rank of both is as of now 0? If you carefully see, both the ranks are 0. So if they are equal rank, you can actually connect anyone to anyone. Very, very important. You can go ahead and connect. Either you can connect like 1 here, or either you can connect 2. It is completely your choice. So what you do is you will go ahead and take this 2 and say, can you please connect with, or I can change the color. Can you please connect with 2? And you'll go to that. Now your above parent is 1. Now remember, you connected 2 to 1, right? Both of them had same level. Both of them were equal height. So you took it and connected. So the height increased. And if the height increased, the rank will also increase by 1. The rank will also increase by 1. Done? Perfect. Next, 2, 3. And this is where again the next thing comes. Who is the ultimate parent of 2? Let's see who's the ultimate parent of 2. It's 1 over here. And is the 1 the top guy? It is. So the ultimate parent of 2 is 1. Who is the ultimate parent of 3? 3 itself. What's the rank? Rank of this particular 1 is 1. Rank of this particular 3 is 3. If you see 1 is 1, 3 is 0. Sorry, it will be 0. Who is the greater guy? This one. So 3 will come up and get connected to the smaller guy comes up and gets connected to the larger one. So 3 is connected to this. Now I'll go and erase this. Connected. Do I do anything to the ranks? No, you will not do anything to the ranks. Why? Because it still has a height of 1, because you connected a smaller to the larger. So the larger is not going to increase. It's not going to increase. So thereby we keep the same height. Perfect. Next, connect 4 and 5. Who is the ultimate parent of 4? 4 is the ultimate parent of 5. 5. What's the rank? 0, 0. Connect anyone to anyone. So what I'll do is I'll go ahead and connect 5 to 4 and I'll erase this. I'll update the parent of 5 to 4. And the other thing that, by the way, I forgot to update the parent of 3. It will be 1. So what the other thing I'll do is I'll increase the rank by 1 because two same guys connected, height increases. So done. Perfect. Next, connect. So what is the next thing? Connect 6 and 7. So ultimate parent of 6 is 6, ultimate parent of 7 is 7. The ranks are 0. So what you'll do is you will connect 7 to 6. You'll update 7's parent to 6. You'll update the rank of 6 to 1. This is how you can easily connect them. Perfect. Done. So apparently I can just remove this as well. So as of now, this is where we stand. What's the next thing? It says connect 5 and 6. So perfect. So who is the ultimate parent of 5? Let's see. Ultimate parent of 5. 5 is here. So 5's parent is 4. Who is actually the top boss? Who's actually the top boss? So he's the ultimate parent. Now I've been asked to connect 6. So 6's parent is 6. 6's parent is 6 himself. So ultimate parent is 6. Let's write the rank. Rank of 4, if you see, is 1. Rank of 6, if you see, is 1. Do you agree? You do agree. So apparently, I can say that, okay, fine. We have someone of the same ranks. So either this can go and get attached here, or either this can go and attach here. So you can do as you wish. So what I'll do is, I will just go ahead and take the 6 and make it attached to 7. To 4. Done. And now I'll omit this. Remember one thing. You attached 6 to 4. So the parent of 6 will be 4. The parent of 6 will be 4. Remember this very, very well. Okay. Next, what is the other thing that you will do? You will have to increase the rank. Why? Because you had 4, 5. You had 6, 7. Both of the ranks, if you carefully see, 4 and 6 had a rank 1. So since you attached same guys, height will, if you see the height increased, so apparently you go ahead and say the rank to increase by 1 more, so the rank will be 2. So this is where we stand till we have not performed the last step. Now, you've kind of understood everything. Now, suddenly if someone comes up and says, does, let me write it, does 1 and 7 or do 1 and 7 belong to same compo? If I ask you this question, the answer is no. But how will you find out? This is where something like find parent will help. This is where something like find parent will come into picture. Okay, so since I'm saying find parent will come into picture, let's understand. So when I'm saying does 1 and 7 belong to the same component, I look at the parent of 1, it's 1. I look at the parent of 7, it is 6. So I'll be like, okay, the parents are different, they are not. But wait, you should not do like this. Just imagine you were having an 8 here. Imagine. Right? I'll ask, does 8 and 7 belong to the same component? Now, something to notice, we are not creating a graph. We are creating a different data structure over here. A graph is not being created. Okay? A different data structure is being created. If I ask you if 8 and 7 belong to the same component, ideally they should. But if you will look at the parent, then 8 would have stored 5, 7 would have stored 6. Both have different parents. Can you actually tell on the basis of parents? Or do you need the ultimate parent, the top guy, the boss? You need the boss, you need the ultimate parent. So this is why, if I'm asking you who's the parent of 7, you say the parent of 7 is 4. So you go 7 and you say 6. You see 6, you see 4. You see 4, you see 4. Oh, I'm the boss. That's why my parent is me. That's why you say the parent, ultimate parent, boss is 4. And the boss for 1 is 1. So both have different ultimate parents. If both have different ultimate parents, you say they do not belong to the same component. This is the use of find parent. Now, since you are creating a kind of a tree structure, the tree will increase in depth with more number of edge additions. The tree will increase. So it will end up taking log n. It is theoretically proven. The tree will increase and it will end up taking logarithmic of n if you just apply union by rank. Because in order to find the parent of 7, you have to go from 7 to 6. From 6, you have to go to 4. And at 4, you find he is himself. So you get the top boss or the ultimate parent. That's going to take you a logarithmic of time. But wait, but Striver, you said it works in constant. It does. We apply something as path compression. Okay. So what I do is I say, okay, someone did ask me to find the parent of 7. So what did I do? I went to 6 because 6 was his right father or the next parent, and six's parent was 4. And 4 says, I'm the parent. So you can write something like this. Okay, I went from 7 to 6, 6 to 4. So I know the 4 is the parent. So once you have figured out seven's parent is 4, and since we are just dealing with parents, and that is what I require, because our main goal is to figure out who is the ultimate parent. So can I say, once I've gone to 7 to 6 to 4, and once I figured out the parent of 7 is 4, can I actually say, I don't need this link anymore. Or I don't need this link anymore because I know seven's parent is now 4. So can I change seven's parent to 4? I can, because the next time if someone again comes up and says me, hey, does 2 and 7 belong to the same component? And you again go and call find parent, you will not move like 7, 6, 4. Because this time 7 will directly go to 4 and it will find him to be the boss. So you did a path compression. You did a path compression. You said, once I will just compress you. And then I know that, hey, listen, your parent is this guy. I know this. I don't need to go via 6. Imagine the tree to be longer. Imagine the tree was something like this. Just imagine. Take it as an imagination. Imagine the tree was something like this. And someone said, find parent of 5. So what will you ideally do? You'll go to 5, you'll go to 4, you'll go to 3, you'll go to 2, you'll go to 1. And at 1, you'll find he's the parent himself. And you'll say, 1 is the parent. You'll say, 1 is the parent. But what I will do is, I'll do a path compression. I know 1 is the parent. And 1 will be the parent of 2 also. So I'll say 2 is directly connected. 1 will be the ultimate parent of 3 as well. So I'll say 1 will be the ultimate parent of 4 as well. So I'll just remove this and say, and I know 5's ultimate parent will be 1. So apparently, a tree which was something like this, if you do path compression on finding parent of 5, 4, 3, 2, 1, and you get 2 as the parent, it returns 2. Sorry, it returns 1. It returns 1. It returns 1. It returns 1. Because you went, and you backtrack to get 1, 1, 1. So what I'll do is, when this guy will return, basically when this guy will return 1, I'll say 3, your ultimate parent is 1. Why are you connected to 2? Why are you wasting your time getting connected to 2? 3 will be like, yes, does make sense. Let me connect to 1. 4 will be like, yes, I'm also wasting time. 5 will be like, I'm wasting time. Everyone goes and gets connected. So this is how the graph will change. Now, under 1, we will have 2, we will have 3, we will have 4, we will have 5 directly. Yes. So, this is for sure. And next time when someone comes up and says, find parent of 4, I'll be like, array, 1. Direct, low, 1. Because 4 is connected to 1 and 1 is the ultimate parent. Someone comes up and says, find parent of 5. Take 1. 1 is directly connected. Ultimate parent. So this is what the path compression technique is. If someone is asking me parent, everyone in the path whom I encounter, I'll replace their links and attach it to the direct parent. But here comes a slight twist. I'll attach it to the direct parent, so it's fine. So what we usually do is we attach it to the direct parent, and that's what we call as path compression. Okay, remember this. So as of now, we have something like this. Now what will happen is the next 3 and 7 will come. So I'll be like, you have to attach 3 and 7. So we know 3's ultimate parent is 1, and that's very easily found because 3 is directly attached to 1. But when I try to find out the 7, I'll have to find the parent of 7, which goes to 6, which goes to 4. And in order to find the parent, we will end up doing a path compression. So let's be honest. Let's do the path compression. which will be something like this. And I'll find the ultimate parent of 7 to be 4, who is connected to himself, right? But if you do this, the tree will be something like this. And the rank of 4, if you carefully observe, is 2. But actually, you have 5, 6, and 7. Ideally, the rank will also decrease, but we cannot do it. We cannot do it because we're not sure of it. Because the rank cannot be reduced in while path compression. The simple reason is, imagine you had something like this and someone asked you to find parent of 8. So you went ahead and found parent of 8 and path compressed. So you reduced one section of the tree, but the other section is still having a bigger length. So the rank cannot be uh, cannot be reduced. So that's why we call it as a rank and not height. If we can reduce it, we would have called it as a height. But since it cannot be reduced, we call it as a rank. Rank in the sense means this guy is bigger than this guy. Sorry, opposite. This guy is bigger than this guy. That's it. That's the meaning of rank. This guy is higher ranked than me. Got it? So the moment you find the parent of 7 to be 4, I find the rank to be 2, which means this is the bigger guy. So the smaller guy will this time come up and get attached to this guy. So what will happen is this guy will come up and get attached to this one. So ultimately what we will have is the parent of 7 will be 4 and I'll attach 1 to 4. So what will happen? The parent of 1 will now become 4, correct? So if I just draw it, it's going to look something like this. 1 attached here and 2 and 3 attached to this guy, correct? So will the rank change? No, it's still the larger guy. Attaching a smaller to the larger guy will not impact because the rank of 1, if you remember, was 1, the rank of 4 was 2. So we are not storing the height because during path compression, the height will shrink. So this is how easily we can do it. Now, if after this someone comes up and says, hey, does 3 and 6 belong to the same component? What you'll do? You'll call the find parent for 3 and it will find you the parent to be ultimate. 3, 1, 1, 4, 4 himself. So again, a path compression will happen. Yes. When you find the parent, 3 will give you as 4. So the path compression will also happen. Find parent of 3 will give you 4. Find parent of 6 will be directly 4. So both of them have same parent or ultimate parent. So they belong to the same component. Quite easy. Since you're compressing the tree, the tree will be always of very limited size. In order to find parent, you have to do limited traversals. Always. Got it? So thereby the time complexity in order to perform the union operation is BGO of 4 alpha. Now this 4 alpha has a huge mathematic derivation which is not required in interviews. You can say 4 alpha, which is as good as constant because the alpha's value is very, very close to 1. So it is as good as a constant. And in order to find parent, it is also 4 alpha. So overall, the data structure works in BGO of 4 alpha. Remember this, okay? So the question comes up, but Striver, how do we do path compression? You might be thinking, how do you do path compression? Because it looks scary because if you are connected to this, then you're connected to this, then you're connected to this, then you're connected to this, how do you path compress it? It's very simple. So 5's parent is 4, 4's parent is 3, 3's parent is 2, 2's parent is 1, and 1's parent is 1. So what you can do is you can backtrack. So you can write something as find parent and you can give the node u. Okay. And what will happen is you will say if u is equal to parent of u, then return this u. So basically, what does this mean? If at any moment 1 comes, 1 will be equal to parent of 1 because parent of 1 is himself. So I'll return the parent as 1. That's the base case because that is where you stop. Otherwise, you will be like, can you please return find parent of u? What does this mean? Imagine I give you 5. What will happen? It will go and say parent of 5. What's parent of 5? 4. It will go and say find parent of 4. So the next time find parent of 4 will happen. Does not obey. Again it will say find parent of 4. Who's parent of 4? 3. So it will go on. So the recursion will be something like this. Function of 5 calls function of 4, calls function of 3, calls function of 2, calls function of 1. At 1, the base case is executed. And when it is executed, it returns 1. So this 2, which you would have called here, what you'll do is you'll say parent of u will be 2. So when it will return up, it will return with 1. You'll say, hey, up 1, keep it, right? Keep it 1. Next, you will again return 1. You'll again return 1. So now 3 will also keep 1. Parent of 3 is 1. Next, you'll also return 1. So now parent of 4 will also be 1. Next, you'll also return 1. So parent of 5 is equal to 1. So everyone in term will assign 1 to it. If everyone assigns 1 to it, so automatically all the links will be path compressed and pointing to 1, and all these links will be destroyed. Perfect. Done. So I hope you have understood everything about the union by rank and the path compression. Now it's time to code it up. So I'll try to create the data structure in a class so that going forward in the upcoming problems, we can use that snippet of code to solve almost all the problems. So we have a class of disjoint set. Nothing to worry, like don't get worried about a class. Very simple. It's a very simple thing. What's the initial configuration? Initial configuration required a rank and a parent. So just have it. And declare everything afterwards public. So all the functions can be reused outside. So now go ahead and declare the constructor. What is the construction? What is the constructor rather? So if you remember, I said you initially rank will be marked with zeros, parent will be marked with themselves. That is what we do. So we say rank dot resize of n plus 1 comma 0. Why n plus 1? Imagine it's a 1 based indexing graph. We need the nth index as well. If it's a 0 based, fine, but declaring it as 1 n plus 1 will work for both 1 based as well as 0 based. Similarly, we can define parent dot resize of n plus 1 and we can keep it. And then we can go ahead from 0. Very, very important to go till n for 1 based indexing. And it will be I itself. So this is how the constructor will look like. Now, what does disjoint set give you? It gave you find ultimate parent, right? So this will be the node, and for this you have to find the ultimate parent. So we know one thing: if node is equal to the parent of node, this is the ultimate parent for sure. So you go ahead and return the node. But if it is not, then you call the ultimate parent and say go to its parent and then look for parent. But this is the normal logarithmic guy. We need the path compression. So this is where I can say whenever it returns the value, I'll store it so that in future if someone comes up and does ask me the same question, I can tell him that this is the parent. So this is where the path compression comes in. Path compression done. Next, what I'll do is I'll be like, okay, void union by rank is what I need to implement. Union by rank. So I'll have node u and node v, which I have to combine. So ultimate parent of, I can say ultimate parent of u will be find ultimate parent of u. Similarly, you can say ultimate parent of v will be find ultimate parent of v. Now I can say if ultimate of u is equal to ultimate of v, I can simply return. What does this mean? If they're belonging to the same component, I don't need, right? But if they're not belonging to the same component, I go ahead and the first thing I do is I check if the guy u is smaller than the guy v, right? So if v is the greater guy, the smaller goes and gets attached to the greater guy. So the smaller will now say, okay, I'll go and have the parent as v. No change in rank, because if a smaller guy gets attached to the larger one, there will be no increase, or that still stays the larger, right? Next, else if rank of ultimate of v, if this is the lesser guy, rank of ultimate of u, if this is the lesser guy, then I say the opposite. I say parent of parent of ultimate of v goes and gets attached to u. Perfect, done. But what if they are same? If they're same, I'll say I'll attach v to u. You can do the other way as well. U to v is okay as well. And rank of ultimate of u will increase because that is where I am attaching it to. We attach to u, so the larger one will grow in size. So this is what I'll do. Once I've done this, I can say the union is done. This is how our data structure will look like. How can we use this snippet of code? So I'll just hard code it to show you how can we use it. It's pretty simple. So you can be like disjoint set ds. Whatever is the number of nodes. So in our case, it was 1. So I can have it as disjoint set of 7. So it will call this constructor and have the initial configuration ready for us. Next will be, I'll call it union by rank. And the first thing was 1 comma 2, if you remember in our example, right? So we'll have it 1 comma 2. So I'll quickly add all these things. So next was 2 comma 3, if you remember. Let's add 2 comma 3. Next was 4 comma 5. So let's add 4 comma 5. Next was 6 comma 7. Let's add 6 comma 7. Next was 5 comma 6. Let's add 5 comma 6. And the next was, if you remember well enough from the example, the next was 3 comma 7. So I'll be adding up this. But before adding up 3 comma 7, let's quickly check if 3 and 7 belong to the same component or not. Same or not. Okay, so what I'll do is I'll call the find ultimate parent for 3 and I will say, okay, do you have equal to 7? Like, do you belong to the same, like, do you have the same boss, same ultimate parent? If you do, then same, I'll say same, or else I will say not same. I'll go and say not same, right? Perfect, done. And after connecting them, I will again check for the same. So as of now, let's have a quick run and see if it is giving us correct answer. So I'll just go and compile this. So on compiling, it is saying, no, they do not belong to the same. And if I go ahead and move it to the next guy, it will actually say that they belong to the same. See, first time it says not same. Then on combining, it says same. So this is how you can always use the data structure. If you want to have two disjoint set data structure, you can go as ds1. You can have two different objects of this class, and you can have two different graphs and two different data structures. So this code can always be reused in almost all the problems because it covers up zero-based indexing graphs as well as one-based indexing graphs. Now a question might be coming to your head, but Trevor, we did not understand why connect smaller to larger. Like, what's the idea of connecting smaller to larger? The first idea is I don't want to increase the height. For an example, if I have 1, 2, I have a 3, 4, 5. Just for an example, I'm taking. So if I connect the larger to the smaller, see what will happen. 1, 2, 3, 4, 5, 6. So basically, the height increases. And if the height increases, like we will do path compression for sure, but if the height increases, what happens is, now in order to find the parent of 6, we'll have to travel 6, 5, 4, 3, and then 1. So we're taking a longer distance. So imagine someone would have said for 4. So you're actually taking a longer distance. And if you do the opposite way, which is saying, let's connect, like you keep 3, 4, 5, 6, and let's connect 1 and 2. So if you see for 6, the distance taken is shorter. Even for 5, the distance taken is shorter. Even for 4, the distance taken is shorter. But for these, the distance will increase. Like for 2, the distance will be now more because over here 2 was just traveling once and getting the ultimate. But over here, it has to travel to 1, then to 3. But the number of nodes over here are lesser. So the travel time for all the nodes computed will be lesser. Over here, the number of nodes are larger. The travel time for all the nodes will be larger. So to give you a clear vision, imagine we had something like this. Imagine, okay, 5, 6, 7, 8. Okay. And we had 1, 2. Now, if you attach this guy to this guy, what will happen is, in order to find the parent of 7, 7 will go to 6, to 4, 3, to 1. Similarly for 8, 6, 4, 3, 1. Similarly for 5, 4, 3, 1. Right? So this will take longer time. This will take longer time. This will take longer time. More nodes will take longer time. Whereas if you attach this to this, they will take the similar time that they were taking. And only 2 nodes will take slightly longer time, which is okay. This is the reason we attach smaller to larger. First, to keep it shrinked. Second is to make sure that the time taken in finding out the parents is as minimal as possible. So you must be thinking, Striver, if that's the case, why are we using something like union by rank? Because after path compression, it doesn't even gives us the height because the height is distorted after path compression. Can we use something as size which keeps a track of what is the size of the component? I think we can. I think we can. So that's what we will be doing. Okay. So what I will try to teach you now is union by size. We know find parent, we know path compression, but instead of rank, we'll be using the union by size. So over here, the same thing will happen. We will have a size array of the same size. So let's quickly declare the size array of 7 size. So the initial configuration will be very straightforward. We will have a size and everyone will be of size 1. Why? Because everyone is itself a component when we start off with. So everyone is going to be having a size of 1. And we know one more thing, that the parent will be themselves. So this is what we take. Now to start off with, very simple. We say 1 comma 2. We say 1 has a size of 1, 2 also has a size of 1. So both are similar size. So it doesn't matter whom you attach. So I go ahead and attach 2 over here. The moment you attach 2 to 1, the size of 1 will increase to 2 because it took a size of 1, got attached to it, so the size increased by it. Okay. Next is 2 to 3. Very important point to realize. Now 1 has a size of 2. And remember the parent of 2 is this time 1. So 1 has a size of 2 and 3 has a size of 1. So this is the smaller. Goes and gets attached to 1. So goes and gets attached to 1. So the size will again increase by 1. Why? Because 3 was a size of 1. Perfect. Done. And 3 will be having a parent of 1. So this is also done. Next is 4 and 5. So what I'll do is I'll just omit this and I'll just assign 5 to this guy. And 5's parent will be 4 and 4 will increase the size of 2. Next will be 6 and 7. So I'll assign over here. I'll assign 7's parent to 6 and I'll increase the size over here. Perfect. Done. Next is where you understand. So next is, so 6 comma 7 is done. Next is 5 comma 6. So where is 5? 5 is here with 4 and 6 is here. So both of them, if you see, are of size 2, size 2, same size. So what you'll do is probably you can take 6 and get attached to this. Done. So 6's parent will be 4. 6's parent will be 4. And since you're attaching a size 2 to 4, the size will increase by 2, not by 1. So basically, this is keeping a track of how big is this. This is keeping a track of how big is this. This is also done. Next will be 3 comma 7. So for 3, it's 1, which is a size of 3 size component. For 7, if you see 7 has this, which is nothing but a 4 size component. So this is a smaller one, so this will go and attach. So when you try to find the ultimate parent of 7, definitely path compression will happen. Here's the first step. Next, for 3, the parent is 1, so this goes and attach. 4's size will be increased by 3. The 4 will be having a size of 7. So you can keep a track of size. And this actually is much more like intuitive, you can say, instead of the rank. I don't find the rank to be that much intuitive, but I find this union by size to be much more intuitive than union by rank because it kind of makes sense when you are storing the size because rank is distorted. So what I'll do is I'll try to copy the same thing. So I'll try to copy the same thing and I'll create in the same function. I'll just create union by size because everything else will stay same. Union by size. And now what I'll do is I will say, okay, fine. I know one thing for sure. Now I'm doing a comparison on the size. So size of this, if lesser than size of this, then I'll be like, okay, I will take the ULPU attached to the ultimate parent of V. Done. Next, the size of the ultimate parent of V, because it is getting attached to, will be increased by ultimate parent of U. Else, now will there be an equal case? If there is an equal case, you still attach it, right? So we can just write an else instead of writing else if greater and then else, because in equal, it doesn't matter whom you attach to, right? So I'll just take this and I'll just change this to V. I'll change this to U. I'll change this to U and I'll change this to V. That's it. So this is how the union by size will work. And what I'll do is, now remember, if you're implementing a data structure, either use by rank or either use by size. Don't use both of them together. Don't use both of them together because we have to declare a size this time. So let's quickly declare a size. And over here, what I can say is size dot resize n plus 1. And I can go ahead and say size of I is initially 1. That's the initial configuration. Then I've written the union by size. Then I have everything as union by size. Let's quickly do a compile and see if it is working fine. Okay, looks like a mistake. Oh, my bad. Comma here. Okay, cool. Should be fine. Okay, not same, not same. Strange. So over here, there was a V, you have to make it U. Okay, now we can compile and see if it is running fine. Yes, not same and C. So this is how you can easily create a snippet of code which has union by rank as well as union by size. What is the time complexity? Which one is better? Both are of the same time complexity because we are still attaching them, still creating trees, still having the path compression. So both of them will take big of 4 alpha, which is as good as a constant. Will like will the interviewer ask you about for alpha? No, because it has a very huge mathematic derivation. You can probably Google and read about it. For interviews, if you tell them that 4 alpha is near about constant, that's more than okay, because what they look for is, do you know the logic? Do you understand this in depth or not? That, please focus on that part as much as you can. So yeah, before ending up this video, I was checking out our channel stats. Nearly 50% of the people who watch our videos do not subscribe to us. So please do consider subscribing to us. It's a very honest request. And yes, if you understood union by rank, union by size, path compression, the code snippet, I think you should hit that like button. And if you haven't checked out our DP series and the SD sheet, the links will be in the description. Please make sure you check them out. And with this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye bye. Take care.